You trying to play the girl?
Huh?
Are you trying to play guys off
I'm
yourself?
trying to play it on myself.
The chapter that it's because he forgot to in disarray.
All right. Okay. All right, it's 5:30. Let's go ahead and get started. All right, good evening, everyone. How's everyone feeling today? I know the homework. I know it's a doozy. That's why I gave it to you guys 2 weeks ago. But I know you guys are busy, so it's hard to kind of do it ahead. But yeah, it's. Wait, say again? No. You need to
extend it.
No. So you need to do it to get practice for the exam. That's the whole point, right? And so my hope is that after you do this homework assignment, the exam is going to be on reads. Okay, that's kind of what I'm hoping. Right? All right, and so with that said, I know everyone's been working hard on the homework. I've gotten a lot of questions about it over the last few days. Our exam is Thursday, and so our exam is going to be very similar to the homeworks. The only difference is that on the exam, I'm not going to have you do any kind of solutions. So I mentioned this in the review video, but for the exam, you're going to be just responsible for computing the element stiffness matrices, assembling it into one system, and applying the boundary conditions, and then that's it. Okay. And so hopefully that makes it a bit easier. Still a little bit tedious because you have to do a lot of writing, but less tedious than the homework where you're kind of checking against my solutions. Okay. One other announcement I want to make regarding the homework. I've gotten a lot of questions on this, and then I didn't realize it until today that I forgot to fix it. But problem 3B on the homework is, so the history behind that problem is that used to be an exam problem, maybe about 2 years ago. And like I just told you on the exam, I don't actually have you solve for the solution. I just have you set up the problem. And so I didn't realize that the geometry for problem 3B is actually unstable. And so if you try to actually solve it, you might get warnings from MATLAB saying that the matrix is singular. You might get NaNs for your solution, and that's not your fault. That's purely my fault. And so that's because that geometry just is not stable. And so all that really means is that if you try to build that structure in reality, it would just kind of fall apart because geometrically it's just not. It just doesn't work out that way. So for 3B, I still want you to set it up. I still want you to do it. But if you're getting solutions that are not valid, then that's the reason why. The only reason I was able to get solutions when I did this by hand was because I've kind of fiddled with my MATLAB settings so that it doesn't check precision as heavily as probably you guys are doing. And so it's able to produce a solution because I basically said, I don't care MATLAB, just find me a solution. And then that's kind of how it is. And so if you're doing 3B and you're getting a singular matrix, don't worry about it. Just kind of set it up and then just kind of move on from there. Okay. All right. And so I think in the email today too, I reminded everyone of the format for the exam. And so remember, you're allowed to bring a writing utensil. You're allowed to bring a calculator. You will definitely need the calculator, so don't forget the calculator, as well as a cheat sheet. And so my policy for cheat sheets is that it's an 8.5 by 11 sheet of paper. And so this size here, you can write on both sides, front and back. You can write it, you can type it, whatever. Okay. And it's going to take place in class on Thursday. Okay. So I have a lot of fun exams. I have your guys' class and I have biomechanics, my previous class. I'll have lots of fun exams to grade over Thanksgiving. So that'll be a fun thing for me. Okay. Thursday, 5:30 p.m., not a.m. No, I don't wake up that early. Question. How to make it easier for me to grade our exam? No, don't worry about it. You don't have to worry about it. I'm okay. You guys just worry about taking the exam. All right. So today I want to cover something that's unrelated to direct stiffness. So we're all done with direct stiffness. I'm not going to talk about it anymore in the lecture. And so I'm getting kind of back to ANSYS stuff. Okay. And so with that said, the semester is kind of quickly winding down. And so after the Thanksgiving, we'll only have 2 more weeks. I do want to save some time after Thanksgiving to just have project work days too. And so everything that we cover from here on out is just going to be kind of just extra kind of practical stuff. Okay. And so, you can kind of almost think of it, we're basically done with the class. We're just kind of covering extra stuff while you guys are working on the project and the midterm and everything. And so today we're going to learn verification and validation. And so some people call this V&V. And so even though I just got done saying this is extra stuff, this is actually really, really important. And so this is important for practical finite elements, but maybe not so much in kind of the operation of finite elements. And so we'll learn about that today. We'll learn about how to conduct these tests and kind of what they're mostly used for. Okay, and so that's all my announcements. Are there any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. And let's cover verification and validation. Okay, so let me start by saying that, all throughout this class, we've kind of seen and we've kind of seen firsthand that finite elements could be a very, very powerful tool for engineering analysis. Okay? Okay. And kind of its most powerful use is that it allows us to simulate situations, real life physical situations, and determine things like the deformation and the stress without actually having to conduct those physical tests ourselves. Okay. And so that's great, right? And so any kind of, any kind of way that we can perform analysis without having to do a physical test, that's going to save us a lot of time. That's going to save us a lot of money. It's going to be a lot more pleasant. You can do it from the comfort of your office, which is, either air conditioned on a hot day or heated theoretically on a cold day like this. And so, it's nice. Okay. But one thing I always want you guys to remember is that FEA is not, it's not God. Okay, so FEA is just, it's a tool, right? And just like any other tool, every tool has its limitations, and not every tool is going to work for every kind of job. Okay. Okay. And most importantly, I think, which is relevant for, especially when you're kind of first starting out, is that FEA is not always going to give you the right answer. And so in other words, it's not going to give you, a perfect representation of reality. Okay. And in fact, sometimes it's going to give you the wrong results, right? So depending on how you set up your mesh, depending on how you set up your boundary conditions, there's lots of ways for FEA to go wrong, okay? And so it's really important that, when you're using FEA, you're always kind of trying to be critical of the results. And so you don't take the results as face value. You always kind of ask yourself, does this make sense? Is this the right thing? Or did I set it up incorrectly? And so what we're going to learn today through verification and validation is kind of systematic ways, or I would say the standardized ways that most people kind of criticize their own work, and then they kind of check to make sure that what they're getting from FEA actually makes sense and is actually correct. Okay, so that's kind of the point of verification and validation. Okay. And so with that, let's make another definition. And so another kind of term that we can use for FEA, it's kind of a more broad term. It encompasses more than just FEA, is that we can call FEA a model. And so when I say model here, what I mean is it's basically a way, it's basically something that can give you a prediction of reality without actually going out and measuring it and testing yourself. Okay. So for example, and so let's consider kind of a real life situation that you can model in FEA. Okay. And so let's say that we're interested, and very simply, we're interested in finding out the maximum amount of force that you can apply on a cantilever beam. Okay. So we want to find the maximum amount of force that we can apply before the beam starts yielding. So we can draw a visualization of this. Okay. So let's say we have our beam here. Okay. And then at the end of the beam, we can apply a transverse load, F. Okay. And we want to find what's the value of F, that we can apply in this beam before it starts to yield. Okay. So what is F max? So this is, a fairly straightforward problem. And so, probably at this point, you guys are very well equipped to do this in ANSYS. Okay. And so if we were to answer this question in ANSYS, we would, we'd first set up a CAD model. And so we make a simple CAD model for a beam. We load it into ANSYS. We apply a mesh. We apply the boundary conditions. So we fix one side, we apply force on the other, and then we gradually increase the force until the equivalent stress exceeds that, it exceeds the yield strength of the material. Okay. Okay. And so that's just kind of a brief summary of how we would set this up in ANSYS. Okay. And I have no doubt that everyone in the class can do this at this point. Okay. And so what you would obtain here from this ANSYS simulation is that ANSYS is a model or a prediction of what the maximum F could be. Okay. So that's all a model means. So a model means that you have a physical question or a question about a physical system that you want to answer, but you don't want to basically do a physical test to do it. And so you do some kind of simulation or mathematical modeling in order to answer that. Okay. So ANSYS here provides the model for us to answer this physical question. But ANSYS is not the only model out there. And so there's other ways that we can perform a model or we can form a prediction for this result. Okay. I'll give you a very simple example. And so when I was making this lecture notes, I think this was maybe like 4 years ago, I had a cousin who I still have a cousin. He's still there. But at the time, my cousin was only 4 years old. And so I told him, I said, Jordan, I have this cantilever beam. And what I want to know is how much force I can apply on this beam before the beam starts to yield. And so I said, give me an answer. And so what he said, cousin Jordan, what he said, what cousin Jordan says that F is equal to 5. Okay. I'm like, 5 what? Like, what does the 5 mean? What are the units of 5? It's like, it's just 5. And then he started crying. And then my aunt got mad at me, and then I couldn't ask him anymore. So that's the answer that my cousin gave me, right? And so that's even though it's a very different method than our ANSYS method, this is still a prediction. And so cousin Jordan here is also a model. Right? Because what he did was that we had a physical problem. I asked him a question, and he gave me a prediction to the answer. He's a mathematical model, right? He could be a model. I don't know. He's a good-looking kid. I'm actually seeing him next week for Thanksgiving too. And so he gave us an answer without having to perform a physical test, right? Obviously, there's one model here that's better than the other one, right? It's my cousin. No, it's ANSYS. Right? And so, in the world of models out there, there's some models that are better than others, right? And by better, what we mean is that the model performs it gives us a much more accurate prediction of reality than others. Okay. Okay. So this one's fairly obvious, which one's going to be more accurate than the others. But let's say that you're comparing two different finite element softwares. And so I know one that's kind of rising up in popularity now is SolidWorks. SolidWorks actually has its own FEA software now. So it's SolidWorks, I forget what it's called, SolidWorks Simulate or something like that. And so then it becomes a little bit more gray area. And so which one do you trust more? Like, do you trust ANSYS more, or you trust SolidWorks more? And so are there certain situations where one works better than the other? Right. And so, because of this, because there's so many different models out there for reality, we need to have some kind of systematic, kind of consistent way to assess or to check how good one model is compared to the other. And that's what we are doing with verification and validation. Okay. And so that's kind of the purpose of these tools. And so there's a lot of, there's actually a surprising amount of research that goes into this. And so, it's something that I was actually personally surprised about when I first learned about it, because you think it'd be a simple thing. And so you would just say that, you ran a simulation, you want to see how accurate it is, how close to reality is, and then you're done. But then, there's actually a lot more aspects to it and a lot more nuance that people are still kind of studying and researching to this day. All right, any questions on this? Okay, all right. And so, the subject for today is verification and validation. So they do refer to different things. And so they aren't just two words for the same thing. And so let's talk about those differences. And so let's define verification and let's define validation. Okay. So let's start with verification. And so verification is the process of assessing the numerical accuracy of a simulation relative to the true solution of the underlying equations. Okay. Mouthful. All right. Okay. And so an FEA, as I've kind of said many times in this class, an FEA, what we're solving for is basically solutions to a differential equation. Okay. And so with verification, we want to make sure that the FEA solution that we obtain actually solves that underlying equation. Okay. And so the way that I like to think of verification, I don't really remember that definition. And so the question I like to answer is, are we solving the equations correctly? So is our solution, is that actually a solution to the equation that we're trying to solve? Okay. I'll give you an example of one form of verification that you've actually already used, or many of you have already used. So one example of this is a mesh convergence test. And so, as you perform a mesh convergence test, what a lot of you have already seen, that as you kind of refine the mesh, as you make the mesh smaller and smaller, your solution is actually changing, right? And so as you refine the mesh, you're getting closer and closer to the true solution to the equation. And so the reason I call mesh convergence a kind of a verification step is because the errors that you're getting as a result of the mesh have nothing to do with the physical situation, right? And so it's purely just a numerical thing. It's kind of an error that we introduce by doing the finite element method. So errors of this nature that are just kind of numerical, in nature, I consider those, verification type errors. Okay? And to be fair, because you guys are using an established software, you're not going to run into many verification errors. Verification is actually more of a step for the coders. Right? And so when you're coding a new tool, you're coding up ANSYS or something like that, you might have typos in your code, you might have syntax errors. And so that's going to lead to incorrect solutions to the equations itself. Okay. And so for the most part, as a user, you're not going to worry about verification too much outside of just like a mesh convergence test to make sure that your mesh is good. Okay. But for the most part, verification is handled by the ANSYS company. In theory, all the developers at ANSYS kind of fix all those things for you. At least they should. Granted, how expensive ANSYS is, they better fix all these issues, so there better not be issues like that. Okay. All right, so that's verification. And remember the key phrase that I remember is, is to ask yourself, are we solving the equations correctly? Are we getting the right solution to the equations that we actually want to solve? All right, next we have validation. And so validation is the assessment of accuracy of the mathematical model relative to the realistic observations. Okay. Because remember, what we're hoping to achieve with FEA, we're hoping that our FEA is an accurate representation of reality. Okay. And so in validation, what we're comparing is, we're comparing our simulated results to, if we were to recreate that exact simulation in reality. And ideally, they should be exactly the same. So you should get the same deformation, the same stress values as you do in the real life situation. All right, and so just like verification, I have a kind of a simple question that you can ask to kind of kickstart the validation process. And so this is generally what I remember when I want to do validation. Okay? And so when you're doing validation, the main question that you're trying to answer is, are we solving the right equations? Or another question you can ask, did we set up the problem correctly? And so validation is asking kind of more of a, kind of almost like a, more like a theoretical or more like a conceptual kind of error, okay? And so at the very basic level, let's say that you want to solve for, let's say that we want to solve our cantilever beam question from earlier, right? You're not going to get the answer to that problem if you set up a thermal simulation, right? And so if you set up steady state thermal and you're trying to find the deflection of a beam, you're going to be very disappointed because, you're not going to get deflection from a thermal simulation, right? And so in that situation, you're solving the wrong equation for the question that you're trying to answer, okay? But most of the time, most people don't make mistakes like that. And so most people are not going to be solving the completely wrong equation, okay? And so a more nuanced or kind of a more common validation question is, do we set up the right boundary conditions? And so remember, the boundary conditions, they have to accurately represent kind of the physical kind of constraints and physical loads that your part is going to be undergoing. It doesn't matter how good your mesh is. You could have a billion elements in your mesh, but if you constrain your part in the wrong location, you're always going to get the wrong solution because you're just not setting up the problem correctly, right? And so if you try to fix your part, in one location, but in reality it's fixed another one, you're always going to get a simulation result that doesn't match reality. Okay, so boundary conditions, I would say, are probably the number one source of error in terms of validation. Right. And so remember to kind of summarize, for verification, you want to ask, you're asking yourself, are we solving the equations correctly? And for validation, you're asking, are we even solving the right equations, or are we setting up the problem correctly? Okay. And it goes even beyond this too. And so, I've actually had conversations with quite a few of you this semester, talk about your final projects. And so for a lot of you, your final projects, or the ones that you want to do, actually incorporate more than one type of physics, okay? And so for some people, I know you want to do like a physics, like fluid and structure interaction. Okay, so you need to simulate both fluids and solids. For some of you, it's thermal and solids. And so you need to solve a thermal problem and then have that be an input to a solid problem, okay? And so choosing, what combination of physics to use for which problem, whether you're going to make assumptions or not, there's a lot of kind of nuance to this, and there's a lot of different ways that things can go wrong. And so, validation is a really important question to ask and really important to check, for your simulations. All right. Any questions on this? Okay. All right. And so the good news for you is that, because you are using an established software in ANSYS, a lot of the V&V work has already been done for you. That's kind of what you're paying for, right? And so you're paying for the company to do all that work for you. You know, otherwise you might as well just write the code yourself, right? That said, you know, there are still some important steps that you can do for every individual simulation that you do. Some of these you guys are doing already, so mesh convergence test is definitely a good one. But it's also good to kind of validate your results against something else. And so that's what we're going to discuss today. And so we're going to discuss, you know, what are the checks that you can do? What are the most common ones? And what you can do under certain situations. So there are some cases where you can perform really nice validation and really kind of increase the faith in your results. But there's some situations where you're not going to have a lot of data. And so, you know, and so we're going to talk about what you can do in those situations. Okay. And I will say that, you know, for a lot of, I would say, professional finite element work done, you always have to do some degree of V&V. Okay. Because remember, you know, you know, we talked about this with the midterm project and the final project. You know, your goal in finite element is not just to do the simulation, but it's you're going to spend more of your time convincing people that your simulation results are actually valid. Okay, and V&V actually gives you a lot of great tools that you can use to persuade people that your simulation results are reliable. And so, you know, I say that, you know, because I don't want you to look at V&V as something that's a hassle or something that you kind of have to do. And so it's really there to help you. It's there, you know, to basically help convince people that you actually know what you're doing. Okay. Because without it, you know, you might as well just be playing video games. And so it's not something, you're producing FEA, but it's, you know, if people aren't going to listen to your results, it's mostly going to be useless. Okay. All right, so let's go over some of the more practical things that you can do for your simulations to kind of help convince people that you're good. Okay. So first is verification. And so we've already talked about this quite a bit, so I'm not going to spend too much time on it. But the main thing that you can do is mesh convergence tests. All right, and so the idea with a mesh convergence test is that you're going to refine your mesh enough so that you kind of eliminate any kind of errors in the mesh. Okay. Okay. Because as we've kind of learned up to this point, you know, the more coarse your mesh is, the less elements that you have, you expect the result to be less accurate. Okay. So generally what you can expect is something like this. So you can have a plot like this. Okay. And on the x-axis, we have the number of elements. Y-axis here, we have the quantity of interest. Okay, so this might be like a deformation, it might be a stress. Okay. And so you're going to run the simulation at multiple different mesh densities. You might get something that looks like this. And so ideally, you're going to reach a point, usually at some point right here, where the solution is not changing anymore as you refine the mesh more. Okay. Because let's say that you use a mesh somewhere in this area. Okay, so let's say that we use this mesh in particular. Okay, and so if we measure the difference between these two, right, that's basically the difference between the solutions if you use that mesh. Okay, and so this distance here represents an error, right? And so it's a simulated value that's not true to the solutions to the equations. And so we want to eliminate that error as much as possible. So we want to make sure that we're getting as accurate of a solution to the equations as possible by refining the mesh. Okay? And so by performing a mesh convergence test like this, and then saying that, we're going to use this mesh right here, you've basically proven that you've eliminated any kind of issues or any kind of errors that are due to poor meshing. Okay? And so in terms of verification, that's usually the main thing that you have to do. And so if you were writing your own code, there's obviously a lot more that you would have to do. And so if you just want a quick rundown of that, usually when you're writing a new code, there's a lot of published what we call benchmark tests. And so these are kind of difficult math problems that have established solutions. And what you would do is you would run your code on those difficult math problems and try to recreate the expected result. Okay, and so that's one way that you would verify new code. But again, ANSYS has done a lot of that for you. So the only thing that you would have to do in terms of verification would be to run a convergence test like this. All right, any questions on this? So that's verification. Let's talk about validation, which I think is kind of the more interesting one, and the one that's more relevant for your projects. All right. And so remember, the point of validation is that we want to basically check and make sure that the results we're getting matches up with reality. Okay. And so there's lots of different ways that you can do this. And it all depends on how much data that you have available to you. So let's talk about kind of the gold standard of validation that you can do, which is experimental measurements. Okay. And so the best way to check if your simulation matches reality is to actually, test it in reality and compare the results. Okay. Okay. Right, so that's the best way to do it. So you basically set up a physical test, usually in some kind of experimental setup, and then you run a simulation on the exact same thing. And ideally, your simulation results and your real life results should be exactly the same. Okay. And so this particular experiment, it's not done often because, as you can imagine, it's kind of a waste of time because the point of a simulation is to avoid doing the real test. And so if you're doing the real test anyway, then there's no point for the simulation. The only point that it serves is to basically make sure that your simulations are actually producing the same thing as reality. So this is a very controlled experiment, and this is often called a validation experiment. Okay. Where you're kind of deliberately kind of setting up a situation where you compare a simulation result and the exact same situation in real life. Okay. Okay, so as an example, so let's say that we want to validate our cantilever beam simulation. And so the best way to do it is to set up a real life experiment. And so you're going to build a beam. You're going to bolt it to a wall, or you're going to weld it to a wall, or whatever. Okay. You're going to apply a force to the end. And then you're going to measure. And so after you apply the force, you would, maybe take a ruler or something, maybe measure the deflection here. Okay. And then maybe you attach a strain gauge to the cantilever beam, and you measure the strain at some location there. There's a lot more sophisticated ways you can do this. So I will say I'm not an experimental guy. I'm very much just a simulations guy. So I know there's much more sophisticated and probably better ways to set up an experiment, but that's the thing that came to my mind. Okay. Okay, and so in ANSYS, you would set up the exact same situation. Okay? And so you'd set up a beam with the exact same dimensions, so same size, width, length, depth. Okay. Mesh it, of course, because it's a finite element simulation. And you would apply the boundary conditions. So you would fix here, apply mode here. Okay. The mode is going to have the same magnitude as what you did in reality. Okay. And then from the simulation results, you would measure deformation here. Okay. And strain here. So the purpose of validation experiment, you do the exact same thing both in reality and in the computer. Okay? And so if this validation were successful, you would see the exact same results in the simulation and in the real life experiment. Which is like deformation and strain, same strain. Right, so this is kind of the gold standard, and so if you're writing a code from scratch, you're going to be performing a lot of tests like this to make sure or to show people that your results are actually realistically accurate. Okay, and let's say for a minute that you're not getting the same results, right? And so you're running your simulation and you're getting different results than you are in reality. Okay, and so I remember someone told me this, and so when they were first teaching evalidation, so they said if you're getting different results in your simulation compared to reality, said I hate to break it to you, but your simulation is wrong. Reality is not wrong. Reality is always going to be right because it's reality. But there's something wrong with your simulation, and so he said go ahead and check your boundary conditions. Make sure that your boundary conditions are correct. Make sure you're fixing it in this exact same way that it's in reality. Your mode value is the same. It's in the same direction. Check the equations that you're using. Are you using the right equations? Okay. You need to have margin deflections on. Check your material properties, and there's a lot of stuff you can do. Okay. But again, because you're using ANSYS as a user, you're almost never going to be doing this yourself unless you're working at a company that has access to these kinds of tools. Right? And so this is usually overkill for most ANSYS users. And so you're not going to go out and run a validation experiment for every simulation that you do. Okay. Validation experiments are really only designed for kind of the testing phase of a new code. Okay. And so again, this is something that you pay ANSYS a lot to do. So ANSYS has performed a lot of the validations for you. They probably did not perform an exact validation on the exact situation that you're simulating. Okay. But they've probably done enough similar situations to basically assure you that whatever situation that you're throwing in ANSYS, they validated against something that's already done. And so, you can kind of trust that you're getting the real life results. Okay. And so again, the biggest source of errors in this case in terms of validation usually comes from the boundary conditions. And so you want to make sure that you're setting your boundary conditions correctly. Okay. Any questions on this? Okay. And so what if you don't have a validation experiment? What if you don't have experimental results for your exact situation, which is common. That's most people. Right? And so let's talk about how we validate without running experiments. Okay. And so even though you can't run experiments, and most of the time you don't want to, right? That's the whole point of FEA is to not run experiments. And so in those situations, how do you validate your results? How do you make sure that they're good? All right, so one way that you can validate is you can validate against certain limited observations. you may not have done like a full test, but you have observed certain things about your physical subject that you can validate against. Okay? And so I think this is particularly relevant for a lot of your final projects. I know a lot of you are working on your senior design project, and so a lot of you are on like Baja, Formula, Rover, and so you have the physical specimen in front of you that you want to run simulations on. Okay? And so what you can do is you can put that specimen, or you can run a simulation on kind of a normal case that you've already observed in reality, and you can kind of see if you observe the same thing. Okay. All right, so one example of this. So I use this example because this is something that obviously that that the company doesn't want to recreate, or they don't want to run an experiment on. And so if you're familiar with the Space Shuttle Columbia, that was an incident where the space shuttle broke apart on reentry because of a part of the foam insulation broke off during launch, and it damaged the shuttle. And so they had limited observations of this. Yep, no, that's true. Yep, and they've definitely changed the design of space shuttles since then, right? And so they wanted to do that. They wanted to redesign the shuttle so that this doesn't happen. But that's not something that they want to recreate. Okay? But they did have limited observations of it happening. So they had cameras that were kind of on board on the outside of the shuttle that kind of saw the foam broke off, and they saw it impact the wing, and it saw kind of the crater and the damage that it did. Okay. And so based on those limited observations, you can set up a finite element problem, or you can set up some kind of computational modeling to try to recreate those observations. Okay. You may not have exact values of the force. You may not have exact values of the size of things because your camera's at a weird angle, but you can try to recreate those observations as much as possible. Okay. And so for a lot of you, that are working on your final projects, this may be something that's available to you. So if you have some kind of observations, or you have some kind of simple tests that you can get the exact same thing. Okay. Right. Another way that you can validate without running experiments is that you can try to validate against some kind of published experiment that someone else has already done. Okay. Okay. I would say this is a bit more common in research because oftentimes when you're researching finite elements, or you're researching new applications, you're applying FEA to something that may not be normal, or maybe a little bit weird. Okay? And so there's not a lot of data on that because it's something weird and only, only weird researchers ever look into them. And so this is actually something that I worked on in my graduate school, was that I was applying FEA to simulate blood flow for specific patients that have gone through coronary artery bypass surgery. And so there's a lot of limited data on that, but there was some published data that we did have. And so I tried to kind of recreate those as best I could, but it's hard. It's not easy to do that. Another option that you can have is that, and this is more common if you're in industry and you work for a bigger company. A lot of times the company will also have kind of their own internal measurements, their own internal kind of published data on certain parts, and you can try to recreate that data using simulations. Yeah. So that could be another option for you as well. So basically any kind of, kind of the point of this is that any kind of real life data, no matter where it comes from, either from observations, maybe someone else has run a test, or maybe, someone else's data, right? Anything that you can use on your physical situation that you can try to recreate in simulations, all of that will kind of further your case. And so all of that will help with validation, just to prove to people that your simulation is giving good results. Okay. All right, any questions on this? Okay. All right, so what if you have none of this? What if you have absolutely no data? And so you're doing FEA on a part that you haven't fabricated yet. It's something that you're in the design phase. How do you validate on something that you don't have a physical specimen for, or you don't have any kind of observations? So let's talk about validation. I call it none of the above. CGI. CGI doesn't exactly follow real life physics most of the time. All right, and so if you don't have real life observations, and so you don't have anything that anything real life that you can compare against, some people would argue that's not really true validation, because validation is you're comparing your simulation results to reality. So ideally, that's what you should have, but we don't. It's very rare that you have kind of an ideal situation. Okay. And so, if there's no real data, it can still be useful to try to validate, not against real life data, but against some other type of calculation. So a lot of times there's going to be some kind of hand calculation that you can perform. And so in all your other classes, you've learned some theoretical knowledge and theoretical equations that can govern a lot of these situations like that we're looking at. Okay. And so to validate against a hand calculation, you would basically try to set up a similar situation with your simple hand calculations, and you try to get the same results. Okay. So it's exactly the same idea as real life data. You have two different types of models. And so, well, in this case, you have two different models. And so you have an FEA model, and you have, I call it a simplified model. So, a model with hand calculations, and you're trying to get the same results on both. Okay. Of course, you're a lot more limited in terms of what you can do with hand calculations. You can't do it on anything too complex. And so what ends up happening is that you end up having to simplify the geometry, and you have to simplify the loadings. Okay. And so sometimes, you have to use your imagination. And so a lot of times your hand calculation is not going to come to you unless you have kind of a very simple situation. And so you might have to be creative. And even if you are able to find a solution to this, or you're able to find a simplified model, your results may still differ quite a bit because, like I said, you're very limited in the hand calculations. And so, there's only so much you can do. And so if you recall from, I think a couple of weeks ago when we talked about the final project, I guess it was last week, part of your final project is to do a validation calculation, okay? And so this is what I mean by that. And so I want you to do a hand calculation on a similar situation as your FEA, and I want you to check your results, okay? And so in a perfect world, what you get from the hand calculation in terms of either deformation, or maybe it's a stress that you're computing with your hand calculation, should be the same as what you get for the FEA, okay? Ideally, but don't be disheartened if you don't get the same thing, because, a lot of your situations that you're looking at for your final projects are way too complex to do in like a straight up hand calculation. I mean, that's why you're doing it for your final project, right? And so, I don't expect you to get perfect matching between your FEA and your validation model, but I at least want you guys to give it a try. So I want you guys to try to find, what's a simplified model, what's a hand calculation here that makes sense relative to my FEA, and let me try to compute something that should be the same, although realistically it's probably not going to be the same because of the limitations. Okay. Okay. Any final questions on this before we wrap it up for today? Okay, all right. So, I probably won't get a chance to say this. I'll try to get to everyone I can on Thursday, but since Thursday is the midterm exam, I want to say just as a group to everyone, I hope you guys enjoy your Thanksgiving break. I know it's a busy time of the semester. It's stressful. It's right before finals, but, try to take some time, unwind, relax, spend time with friends, family, because it's important. You really need to recharge during this time to make sure that, you're kind of staying healthy. So, hope you guys enjoy it. I'll say this with as many people as I can Thursday, but thank you guys for coming today. And I'll see you guys all on Thursday for the exam. Oh yeah, for sure. Yeah. I think that's better for everyone too, so you don't have to study over Thanksgiving.
Final project question.
Yep.
So the background why I don't know how I would do a hand calculation or some sort of
That can come, that can come later, and so you don't have to figure that out yet. So I would rather just see the CAD model and see if that's good. And then you can follow, you can figure out what you need to hand calculation there.
He was looking between. I like to, just wasn't.
Yeah.
Yeah. That's on my
You can find one that's similar too. So it's gonna be, I know you're gonna be really busy the next few weeks, so I don't want you to spend too much time making that. So if you want to find one that's similar, that's, I'm fine with that. Ideally it should be the same, but you have to kind of balance it. I'm not gonna mark you down if you don't get it.
I didn't? I didn't know that.
Okay. Sorry, I think I had the same impression about my homework.
Yeah.
It's just been really busy and we're stressing on time. Like, what exactly are you gonna grade on? 'Cause I want to try to get as maximum amount of points, but at the same
So the
time-
homework, I'm graded the same as I do the activities, so it's graded on completion. And so as long as I can see that you did it, you know, you said you wrote the elements, difference matrices, you assembled it, you applied the bound conditions. Whether you get the exact solution itself is just great. So I'm just looking to see that you gave it a shot for every problem. It's an honest effort. You didn't just like scribble this random stuff.
Yeah, because I'm legitimately trying to set up the whole problem.
Yeah.
Except that it's just like the tightness of time. I'm
Yeah.
just like struggling to.
Yeah. I mean, just set up everything. You know, just say that, you know, this is the setup, and then that's the best. So I have a solution there so that you can check to make sure your setup is correct. But I know you guys are first time, so I want to at least make sure you guys get practice setting it up. And then, you know, if you got the solution, that's great. But I'm not going to mark you down.
Okay, yeah, because it's been a really rough month for.
Oh, I'm sure. This is always the worst time.
Yeah, and like we really do enjoy your class and like the assignments because they're actually really helpful.
Yeah.
It's just our crunching
For
time.
sure. No, yeah.
I just don't want to show that like we don't care. It's like I do really care.
I don't, honestly, I don't, because I know you guys have a billion things going on. And so, you know, even if you don't turn in a homework assignment, I know it's not a reflection of whether you care or not. It's just, you just have a lot of other stuff going on.
There's
That's
one
the reality.
assignment for like.
Yeah,
Right?
and there's one drop. I dropped your lowest score.
Okay. Yeah, because you're in for one.
Yeah. I've had students in the past, but I knew how much the class was. How hard they were working. It's just there was other
Are you
stuff.
staying in here too?
I don't judge on
Staying in
that.
here to do
You know, I don't even. I have to grade the assignments for what it is, but how that, I don't take anything personally.
Thank you.
I didn't do it.
You gotta post the solutions to the homework.
Yes, I will. So before I go to sleep tonight, I'm gonna post the solution, make it, so you can have it for your reference.
So that's the one
Because
thing.
I know 4B is weird.
That is bad.
That's the difficult part of doing problems. So I check along the way, so I don't just keep doing the problem.
For sure.
with the wrong
I have a
thing.
better-
For sure.
Yeah, I got they're the 9L, whatnot, but I have the wrong answer.
Again,
So I see you later, but I saw that the convection company
okay,
put on
awesome.
convection.
Yeah.
It's 9.812 watts per meter squared Kelvin for realistic.
It looks reasonable to
Yeah,
me,
it's the most-
kind of based on what I've seen before, but I mean, every situation is different.
Now we have.
So I'd have to kind of look at the whole, that's, it's not an unreasonable number. It's not too
Yeah,
small,
that's what I
it's not
thought
too
too.
big, it looks reasonable, but, you know, I have to look at it, I have to look at it carefully about. Was your Reynolds number, was it Lambda?
Oh, heck no.
Okay,
I got a
that's good.
Reynolds number of 300.
Yeah, that's
Oh,
what I
yeah,
thought.
that's-
It's going to be that.
Yeah.
Yeah, that's kind of what I, that's kind of what we talked about. So, I mean, that makes sense.
Yeah, I thought so too. And the only thing is, I did the Nusselt correlation based off of a flat plate.
Yeah, no, that's fine. That's what I would
Oh,
do.
this makes sense too, right?
You know, I mean, if you look at it kind of like really small, it's an approximation, but I think it's a fair one. It's a fair one. Exactly.
Okay. Yeah, I think so. And I was working most US customary,
Yeah,
and when I converted, that's what I got. The whole BT stuff is throwing me off.
yeah, I would just convert it all to the SI first.
So I'll work from there. So I did have a question in regards to
Because.
my next simulation. I'm planning to use this for my final project.
Okay, yeah.
So I do have the convection, I have the structural analysis on it, feel like it's work.
Yeah.
Now, I do want to do a conduction from the brake pad over to the
Yes.
friction.
Yeah.
So how do you,
So we need around.
a rotational heat transfer. So
I would just do it the way that we talked about office hours. So I would just apply flux stuff
okay,
based on just the energy. So you know how much energy you're losing as you're.
I see.
So you wouldn't have to worry about conduction.
And then I didn't fly because it's never did it.
That's how much energy, because all that kinetic energy from the remote is being transferred.
Guy that actually saw it.
Yeah.
Yeah.
Got it.
So I would use it right now. I think that's a better.
Okay, yeah, that one is pretty simple too. Thankfully. Awesome.
They were all.
Yeah.
So before, I don't know if I'm sending up the boundaries. When I.
I got,
Yeah.
But I'm not getting the same.
Yeah, Kevin was doing the same thing.
Well, stuff.
Go ahead and send me your work. I need to take a closer look at it and see.
Six of those.
Yeah, because it's a little. I know the numbers for this one. And so go ahead and send me your work. And I'll take a look. I'll go back to my office.
It's just the amount of.
So basically, it's just gonna be this.
Exactly.
And they put the, and then for this one, they really hating this. Dealing with like normal, just like normal, let's convert it into like.
Yes.
Versions. Yeah. So then don't, when you get something different to this, it's not what we so busy to for whatever reason.
Exactly. Yeah.
So.
Yeah.
Still don't do it.
Oh, of course. Okay. Yeah. Yeah. Oh, yeah, it doesn't have to, it could be sometime. Yeah. Hey, Gary.
Hey, just a question for you.
Yeah.
So in December, I'm gonna be up north in Everett.
Okay.
Work. Nice. So my guys are gonna be cruising